Hola, children. Okay, well, I've got my coffee, pumpkin spice, and you asked for an implicit differentiation video, so here it is. Okay, so let's talk about implicit differentiation. We know this. Let me just make this a lot bigger. Okay, if we have a function, 2x plus y equals to 6, that function's really easy for us to solve in terms of y, right? So we solve for y, and we get our function in terms of x, right? And this is because down here I made a note, y is equal to f of x, so it's interchangeable. So all of our functions thus far are in terms of x, right? So when we differentiate, for instance, this function here, you know, we're taking the derivative with respect to x, and I didn't write this down here like I did with the other one, but you know, I can say y prime is equal to the derivative with respect to x of negative 2x plus the derivative with respect to x of 6, right? And this x matches this x, so when we take the derivative we find that it's negative 2, and of course the derivative of 6 is 0, so because you know this is really 6 times x to the 0 power, right? And x to the 0 power is 1, so anyway, we get a negative 2, alright? So we always write our functions, or so far in your whole, you know, mathematical life, you've been writing functions in terms of x, and we differentiate with respect to x. Another simple function, I think I wrote this one on the board or something similar, is, you know, if you think of the function y equals to 6x squared, you know, you can also think of that as x of x. F of x equals 6x squared. Well, if I take the derivative of f prime of x, or y prime, whatever you want to call it, because remember, they mean the same thing, then what we're really saying is what is the derivative with respect to x of 6x squared? And again, these x's, this variable matches that variable, and so we just take the derivative and say it's 12x, and we're done. Okay. Here's the equation of a circle, which I always start the lesson out with, right? Now, I can solve this pretty easily for y, because remember, circles are not functions, right? A circle, this is a circle with its center at the origin and a radius of 4. So there it is, right? We'll call those 4's there, negative 4. A circle's not a function because it fails the vertical line test. So what we do is when we solve this thing, we actually, you know, solve for y, take the square root, we actually get plus or minus, and again, the positive root, 16 minus x squared, in this case would be the upper half of the circle, and the negative root 16 minus x squared would represent the lower half of the circle. That's how you have to graph it in your calculator, the positive and the negative. Alright, so this, we could differentiate, right? We could use the chain rule, right? We could rewrite this like so, do the chain rule, and get the derivative of something like that. But there are many functions that you're not even going to be able to solve for y. For example, this one here. That's impossible to solve for y. You can get the y's on one side and factor out a y, but then you still have a y. You know, if I factored out a y from these two here, then I've got x squared plus 4y. I can't get the y's, you know, I can't make it one y. So many functions are impossible to solve for y, so you wouldn't be able to do something like I did up here with the circle. So the implicit differentiation allows us to differentiate with respect to x, even though our variables aren't all x's, leave things where they are and differentiate term by term, and then solve for y prime by getting it to one side of the equation and getting everything else over to the other side. So, like a moron, I started writing notes so I could talk through them real quick, and I did not get a book. So let me grab a book real quick. Let's see. Let's grab a good calculus book. So many calculus books and so little time. So I'm going to take problems out of Finney's book right here, Finney Calculus. This is an old book, but you know, calculus is calculus. And I'm just going to look up where the implicit differentiation is in this book, because I don't remember. Implicit implicit. Here we go, page 149. Alright, so let me go over there and I'll write down a problem. So, how about we'll start off with something simple. Okay, so for example, y equals 1 minus 6x to the 2/3. Now you might say to yourself, that's not implicit differentiation. Yes, it is. Because with implicit differentiation, we differentiate both sides of the equation, right? So I'm really differentiating it. I know I say y prime is equal to, meaning I'm taking the derivative, but when I do that, I'm really taking the derivative of y with respect to x. So you can think of this thing as the derivative with respect to x of y is equal to the derivative with respect to x of 1 minus 6x to the 2/3. Now, the derivative with respect to x of y, well, this variable does not match that variable. So we take the derivative as though it were just, the derivative of x, which is 1, but we have to multiply it by dy dx. You notice dy dx, or y prime. So I'd say this is y prime equals, now on this side it's easy because this variable matches that variable, so we're just going to differentiate as we would. Chain rule, right? This will give us 2/3 times 1 minus 6x. If we subtract 1, we get negative 1/3. 1/3. So chain rule is derivative of the outer function, put the inner function back in, and then multiply that by derivative of the inside function. And that would be our derivative. Okay? Let's bump it up a notch. So let's do this next problem here, which is x cubed plus y cubed equals 18xy. So what I'm really doing is I'm taking the derivative with respect to x of x cubed plus the derivative with respect to x of y cubed is equal to 18 constant multiple times, now I'm going to be careful here because I got a product, right? So I'm going to do x prime y plus x y prime because it's easier to write it that way. But the derivative of x with, the derivative with respect to x of x cubed, the variables match, so I know it's just 3x squared. Bring down the plus. Here I have a problem. This is x and this is y. So when I have a problem, when the variables don't match, I take the derivative, 3y squared, but I have to multiply it by y prime. Every single time the variables don't match. On the other side, I have 18. Derivative of x is 1 times y is y, plus x times derivative of y is y prime. Now the goal is that we want to get our y primes over to one side of the equation. Okay, so in this case, it was already done for you. You didn't have to move anything. In this case, we're going to have to manipulate it a little bit algebraically. So, no problem, right? What I have here is I'm going to go ahead and distribute this 18. So we have 3x squared plus 3y squared y prime is equal to 18y plus 18xy prime. And I'm going to subtract 18y prime from both sides, and I'm going to subtract 3x squared from both sides. So I'm going to move this 3x over to this side. I'm going to move that over to the left-hand side. So that's going to give us 3y squared y prime minus 18xy prime is equal to 18y, this was already on the right-hand side, minus 3x squared. And then the goal is we're going to factor out that y prime. So we get 3y squared minus 18x is equal to 18y minus 3x squared. And now I can finish this off by dividing both sides by this factor. It's going to cancel over here. And we're done. Okay? So something like this again, you could, let's see how that works. Let's just play around for a second. I could take this function and I could get the y's on one side and the x on the other. So I have y cubed minus 18xy is equal to negative x cubed. I could factor out a y, but then I'm left with y squared minus 18x is equal to negative x cubed. You see, I cannot solve it for y. I can't get y by itself. Blah. So, rather than even trying, unless it's a circle equation, that you can always do. Rather than even trying, just differentiate it piece by piece. Here's another one. Let's use one with a trig function in it. So, how about y is equal to, x is equal to sine of y. So nice and simple. If I differentiate the left side, I get 1. If I differentiate the right side, the derivative of the sine is the cosine of y times y prime. And now I have to solve for y prime, and that's easy. If I divide both sides by the cosine of y, I get y prime, and 1 over the cosine of y is the secant of y. You're done. Likewise, you might have something like x equals to the tangent of y. Again, derivative on the left is 1. Derivative of the tangent of y. So remember, we're taking the derivative with respect to x. So, always think of this. If you get confused, this does not match that. They're not the same. So the derivative of the tangent I know is the secant squared of y times y prime. And so I can write 1 over the secant squared of y is equal to y prime. And the reciprocal, 1 over the secant, goes with the cosine, right? So I could just write that as cosine squared of y is equal to y prime if I want to. This would be simplified. This would give you the points on the test. This would be simplified. Here's another one. There's some crinkle in this paper. It's annoying me. So 6x squared plus 3xy plus 2y squared plus 17y minus 6 equals 0. Let's differentiate. Here we get 12x. Here I've got a product rule, so 3 times x prime y plus xy prime. Alright, plus here I'm going to differentiate. That's going to be 4y prime plus 17y. So if I take the derivative of this term, it's going to be 17y prime. And of course the derivative of 6 is 0, so that whole thing equals 0. Now I haven't applied the product rule yet, I just wrote it out. So I have 12x plus 3 times y plus xy prime plus 4y prime plus 17y prime is equal to 0. And now I'm going to distribute that 3y plus 3xy prime. This is why it's so important to write out every step on the test, so you don't make a mistake, and so I can kind of follow where you're going. That's why no work equals no credit. Alright, so now I've got all my y primes on one side of the equation, and all I'm going to do is move the other pieces. I'm going to move these two over by subtraction. So I've got 3xy prime plus 4y prime plus 17y prime is equal to negative 12x minus 3y. Here I can factor out a y prime, and I'm going to be left with 3x plus 4y plus 17 is equal to the right-hand side. And finally, I can isolate y prime by dividing both sides by that factor. It's a factor because it's multiplied, right? So 3x plus 4y plus 17. Done. Don't try to simplify it. I know on the top you could factor out a 3 and blah blah blah. Just leave it alone. Because most often with implicit differentiation, you're going to have to do something with it. They're going to maybe give you a point and ask you, right, this is the derivative. So if I had a point, say maybe 0, 1, I could find the slope of the tangent line, then I could find the equation of the tangent line. Okay, but we're not going to do that right now. We're going to focus just on the implicit differentiation part. Alright, here's... Okay, let me fix this, and... Sorry, but I had a disturbance. Not a disturbance, but an interruption, so I had to cut out, so we're going to see how this is going to go here. Okay, can we focus? Can we please focus? Is it possible for this thing to focus? Is it? No, maybe it's in too close, so let me try this. Oh, I just had it. Shoot. Sorry, guys. Okay, there we go. Alright, here's another type. Now look, we're going to differentiate every term both sides, right? Here I have a product rule, so I'm going to write out the product rule. I'm not going to take the derivative yet. I'm going to have x squared prime times cosine squared of y plus x squared times cosine squared of y prime minus the derivative of the sine of y is the cosine of y times y prime is 0. Now remember, I'm going to rewrite this further because we know that the cosine squared of anything, x, y, whatever, we can write as the cosine of y quantity squared because we need to use chain rule, and so that's going to make it easier. So I'm going to take the derivative here. We get 2x times cosine squared of y plus x squared. Now if I take the derivative using chain here, I'm going to have 2 recomposed with the inside times derivative of the inside times y prime minus cos y prime equals 0. So I'm just bringing that down. Okay, I got to get my y primes together. So, you know, this whole mess here, that's just one whole thing. So look, 2x cos squared y. I'm going to bring the minus sign out front, and I'm going to put the 2 out front. So minus 2x squared cosine of y sine of y prime minus cosine y prime equals 0. And now I can see that I can get rid of this by subtracting both sides. So I've got negative 2x squared cosine y sine of y prime minus cosine y prime is equal to negative 2x cos squared y. And I'm going to factor out that y prime. I don't care about anything else. So I've got negative 2x squared cos y sine y minus cos y is equal to the right hand side. And now I can solve for y prime. Y prime is equal to negative 2x cosine squared of y all over negative 2x squared cos y sine y minus cos y. And you can keep it in parentheses if you want to. Again, don't go canceling out the negative signs because, remember, there's 2 pieces to this denominator. So this numerator takes on both of those pieces. So you can't just cross out those negatives or those 2's. You've got to be very careful. And by the way, well, anyway, I'm not going to go any further. Just leave it alone, okay? If you get this far, you get full points. So that's the end of that. So that was a little bit more difficult because you had to remember some of your trig rules, and we could simplify this way more, but again, I'm not going to focus on simplification. My goal is to get you to differentiate implicitly so that way you can get y prime by itself, get everything else over to the other side without any errors, and we'll worry about, or we'll work on, simplifying these things later on. Alright, so I hope you found this helpful. I hope you have a great night. Study for your implicit differentiation little test for Thursday, and we'll see you then. Adios!